Hello and welcome you all to the 25th lecture of this course where we are discussing the electroweak interactions in the standard model of particle physics. And so far we have been able to develop the quantum electrodynamics, the Feynman rules, and we have also been able to kind of write the matrix element or the amplitude for some QED processes using those dictionaries of Feynman rules. And today we are going to actually discuss how to find the cross section for some processes in QED, and this is going to be extremely interesting. But before we do that, we have to do some mathematical formalism, and let's go through that, and then we will come back to the cross section derivation. Okay, so let's get started. Let me quickly remind you that for different processes like E plus E minus going to tau plus tau minus, or E minus mu minus going to E minus mu minus, we have been able to write the matrix element or the amplitude which is written here, which you can see. And so for example, for the Compton scattering also we could write the matrix element using the rules that we actually developed. However, when we try to compute the cross section, if you remember the kind of derivations that we did in the initial lectures, the differential cross section will actually involve what you call the matrix element squared, right? So you have to have the matrix element squared. So this is something that we need to calculate. Once we know the matrix element or the amplitude, we need to calculate the mod m square to be able to kind of find out the differential cross section. And in order to do so, we have to use some of the trace technologies. Okay, so first of all, trace of an identity matrix which is 4 cross 4, that will be of course equal to 4, right? Trace of odd gamma matrices, that will be equal to 0. Trace of gamma mu gamma nu, so we have to have the trace of these Dirac matrices, and whenever you have trace of gamma mu gamma nu, that will be equal to 4 of G mu nu. Trace of gamma mu gamma nu gamma rho gamma sigma, what will be this? See, here we will have it like 4 of G mu nu, the first two indices, into G rho sigma, the last two indices, minus 4 of G mu rho, first and third index, into G nu sigma, which is second and fourth index, plus G of mu sigma, first and fourth index, and G nu rho, which is second and third index. Now this is something that I am not proving, but you can go back to any quantum field theory book that you like and you prove this relation. Okay, trace of gamma mu gamma nu gamma rho gamma sigma is equal to 4 G mu nu G rho sigma minus 4 G mu rho into G nu sigma plus 4 G mu sigma G nu rho. Okay, trace of gamma 5. Trace of gamma 5 is identically 0. What was gamma 5? You remember the gamma 5 was I, gamma 0, gamma 1, gamma 2, gamma 3, correct? And this was helpful in identifying those chiral projections of those Dirac fermions. So far in the QED, we do not perhaps require the trace of gamma 5 or any combinations of the Dirac matrices with the gamma 5, but we may require it, or rather we will require it when we discuss the weak interactions. So the trace of gamma mu gamma nu gamma 5, this is also equal to 0. Okay, this will also vanish. However, trace of gamma 5, gamma mu, gamma nu, gamma rho, gamma sigma, that is 4 Dirac matrices along with the gamma 5, this is going to give you something interesting. This is epsilon mu nu rho sigma. What is this epsilon mu nu rho sigma? This is basically completely antisymmetric tensor of rank 4. Antisymmetric tensor of rank 4. इसका मतलब क्या है? It basically means that epsilon, say for example 0, 1, 2, 3, epsilon 1, 2, 3, 0. These are all 1. You know, if you do like epsilon 0, 1, 3, 2, any odd permutation, that will actually give you minus 1. Anything which is repeated like epsilon 0, 0, 1, 1, epsilon 1, 1, 1, 1, all those are going to be identically 0. So, this is what you mean by completely antisymmetric tensor of rank 4. Now, once again, this relation is going to be very, very useful when we actually calculate the cross sections of weak interaction processes, but this is something that you should try deriving. There is another relation that we are going to use, which is the completeness relation of this Dirac spinors. So, sum over S equal to 1 to US P US bar P, that will be given by gamma mu P mu plus M I, where these are all 4 cross 4 matrices, right? I is a 4 cross 4 identity matrix. So, gamma mu P mu is usually written as P slash. So, this is going to be P slash plus M, where you tacitly know that this M has actually one identity matrix along with, which is actually 4 cross 4. So, this is one relation which is going to be very useful. And there is also a completeness relation involving the antiparticle spinors like Vs, and this VSP, Vs bar P, that will be given by gamma mu P mu minus M or P slash minus M when summed over both the spin states like S equal to 1 and 2. Let us check the first relation. Okay. So, let us check S equal to 1 to 2 USP US bar P. इसका मतलब क्या है? U1P U1 bar P plus U2P U2 bar P. Now, what is USP, or what is the particle spinor in the Dirac-Pauli representation in which actually we did all the calculations? You remember these forms, or if you do not remember, you go back to your earlier lectures and find out that your USP was essentially square root of E plus M phi s sigma dot P by E plus M phi s, where phi s can take two possible values. One is phi 1, which is 1 0, and the other is phi 2, which is actually 0 1. So, this will give you U1P and U2P, right. So, this is what USP looks like. Now, once we have the USP, then we can actually find out what is US bar P. US bar P, by definition, you know that this is essentially psi bar is what? Psi dagger gamma 0, correct. So, this will be US dagger gamma 0. What will be US dagger? This will be square root of E plus M, wo to bahar hai. Phi s becomes phi s t, because there is no complex number involved here. So, this is just the transpose. What will happen to sigma dot P by E plus M? That simply becomes sigma dot P dagger by E plus M into phi s transpose. And then gamma 0 in the Dirac-Pauli representation, this is simply I 0 0 minus I, where I is essentially the 2 cross 2 identity matrix, correct. So, this is what we have already seen. Now, if you do this matrix multiplication, how exactly this will come? So, this will become phi s transpose, and this second term will give you minus sigma dot P. Now, the point is sigma dot P dagger is actually sigma dot P. So, this will be minus sigma dot P by E plus M phi s transpose, right. So, we have the US bar P. So, let us now try to do this multiplication USP US bar P. Now, you see that USP is a column matrix, right? It is a column matrix, whereas US bar P is a row matrix. So, basically what happens that when you take US bar P, that basically means that it is going to give you rather a square matrix, right? So, how that you take the first element of USP like phi s, and multiply with the first element of the US bar, which is phi S transpose, and that is going to give you the so-called 1 component of this matrix. So, phi S T. You take the first element and you take the second element of this row matrix of US bar P, which is minus sigma dot P by E plus M phi S T, and that gives you 2 component of this square matrix. Similarly, now you take the second component of USP, which is sigma dot P by E plus M into phi S, this component, and then you multiply this with the first component of US bar P, and that is going to give you the so-called 2 component of this one. And similarly, you take this second component and multiply with the last component or the second component of US bar, and that is going to give you what? This is going to give you minus sigma dot P whole square by E plus M whole square into phi S into phi S T, correct? So, this is exactly how the sum over S equal to 1 comma 2 US bar looks like. Now, sum over S phi S T, you can say that this is nothing but phi 1 transpose plus phi 2 transpose. Once again, it is a phi 1 transpose if you do, because phi 1 is 1 0, phi 1 transpose is 1 0 row matrix. So, when you do, it will give you a 4 cross 4 matrix, that will be 1 0 0 0, and then phi 2 transpose is going to give you 0 0 0 1, and so therefore, when you add, this is going to give you 1 0 0 1. And also what you have is that sigma dot P whole square is nothing but P square, and P square is nothing but E square minus M square, that is E plus M into E minus M, right? And so therefore, now you can use all these ingredients here, that phi S T sum over S, that is nothing but identity, and then sigma dot P whole square is nothing but E plus M into E minus M. So, what does it give? This basically tells you this first entry is going to be simply E plus M into the identity matrix. What happens to the second entry? Because this E plus M gets cancelled, so you only have minus sigma dot P. Identity matrix और लिखने का जरूरत नहीं है यहाँ पे. In this entity, what happens, that E plus M gets cancelled, and what you have, that you have once again sigma dot P, and in the last one your E plus M whole square, वहाँ से E plus M gets cancelled with essentially minus of E plus M into I. And now if you inflate this, you can see that this can simply be written as gamma mu P mu plus M into identity matrix of 4 cross 4 dimension, and that is nothing but P slash plus M. So, this is the completeness relation involving the particle spinors. Similarly, you can do the completeness relation involving anti-particle spinors. You can imagine what exactly this is going to be. VSP Vs bar P is going to be P slash minus M. Okay. So, we will use these ingredients to calculate the matrix element square and the cross section. So, let us go into one such process essentially. So, let us do this process. You remember we actually drew this process like E minus mu minus going to E minus mu minus, and today we are going to look into E minus tau minus to E minus tau minus, and the point is that this is identical to E minus mu minus going to E minus mu minus, excepting for the fact that instead of muon we have actually tau here, but that doesn't bother us too much. So, how to draw the Feynman graph? It is going to be very similar. So, you say that I have an initial state electron and final state electron with momentum P1 and momentum P3 that can have a photon mediation, and this can be connected to the other end of the graph with an incoming tau and an outgoing tau with momentum P2 and P4, right? And so, this is a legitimate diagram, and as per our definition, this is a T channel diagram, just because the momentum which is carried by the photon. So, this is the photon which carries the momentum from this vertex to this vertex. This is like q is P1 minus P3, and according to our definition of the Mandelstam variable, this T is P1 minus P3 whole square. So, this is the only way that I can connect this graph, and this process can be mediated by QED interaction. So, let us try to write the Lorentz invariant matrix element. You know, we use all those technologies, or rather the dictionaries which we actually developed in the last class, and we can easily say that this matrix element square is going to be minus E square by, you know, E square by Q square, right, and this is going to be U E bar P3 gamma mu U E P1. The first part, this is the first current that you have, the electron current, right. U E bar P3 is representing the final state particle that is being produced. U E P1 is the annihilating particle that you have, and similarly I can say that the particle which is being created for the tau sector will be U E bar tau P4, and then I will have the gamma mu, or you know, this is the QED vertex that I usually have, and essentially then I have, you know, U tau P2, correct, and this factors of minus E square is essentially coming from the vertex, because your each vertex essentially is proportional to minus I E gamma mu, and this was proportional to minus I E gamma nu, the different Lorentz index, but on the other hand the propagator was actually proportional to minus I G mu nu by Q square plus I epsilon. I dropped the I epsilon part here, and I essentially has, you know, borrowed this part like minus E square by Q square, and then this is basically, you know, the part involving the spinorial part of this particular process. So, this is the matrix element. Now, what we have to do is to calculate the matrix element squared, right. So, when we need to calculate the unpolarized cross section, suppose when we say that these electrons or the taus which are actually coming to collide with, they do not come with a specific helicity or specific spin projection, that means they are unpolarized, and then what we need to do, that we actually need to sum over all possible, you know, spin and helicity, this sum over is spin and helicity, and also average over the initial state spins. Okay, sum over all possible spin and helicity states and take an average over the initial state spins. So, basically therefore, we focus on something like mod of m bar square, and you this is basically, as I just said, this is average over the initial state spin configurations and sum over all the final state spin or helicity configurations. Now, that is what is legitimate, because initially if you are not mentioning what is this, then basically I will take an average over the spin. So, average is basically summing and dividing by the total number of possibilities. So, this is precisely what I mean, that what is this. So, I have to sum over all possible spin to find this sum over S mod m square, and multiply with 1 by 2s1 plus 1 into 1 by 2s 2 plus 1. Why? Because this is where I mention that S1 and S2 are essentially indicating the initial state spin. So, this factor is what takes care of the fact that this is averaged over the initial state spins or averaged over initial state helicities. Now, we all know that for the process that we actually have, all these particles are actually spin half objects. So, S1 is half and S2 is also equal to half. So, what will be your mod m bar square, which is denoting our you know, so to say, average over the initial state spin and sum over the final state spin. This is going to be essentially factor of 1 by, so 2s 1 plus 1 ये कितना आता है, this is 2, 2s2 plus 1, this is essentially 2. So, this will be 1 by 4 of sum over S mod m square, right. So, this is what we will actually calculate. Now, it is also possible for someone to say that, okay, when I collide these electrons and tau, I want them to come with a specific helicity because I have aligned the spins along to the direction of the motion or in the other way around and so on. And in that case, I cannot take this average which I am doing. So, this is specific to the case when I am not being told what is the initial, spin or helicity combinations for which this cross section is actually sought for. So, if it is not mentioned, then it has to be understood that you are actually trying to find the unpolarized cross section where you sum over all possible spin configurations of the final state spin configurations, and you have to take an average over the initial state spin configuration, and then that is where exactly this factor of 1 by 2 S1 plus 1 into 1 by 2 S2 plus 1, where S1 and S2 defines the initial state spins, has to be taken into account. Now, what exactly this mean basically? What exactly this basically mean in terms of the helicities that we have learned? So, this is equivalent of saying that there are 4 possible initial state helicity combinations that you can actually think of, right? I mean, because we know that the helicities are like right helicities and left helicities. Right helicity is the one where the spin is actually projected along the direction of the motion or along the momenta. Left helicity is the one where the spin is actually aligned opposite to the momenta. So, you have therefore the electron tau combinations will involve 4 helicity combinations. One is of course RR, both are right handed. One is right handed, one is left handed, the other is left handed and the other is right handed, LR basically, and both are left handed. So, if we do pictorially, then it can be that the electron is right handed and the tau is right handed. So, this is specifically the RR combination that you have. On the other hand, you can have the electron right handed, but the tau left handed. That means the spin is aligned opposite to the motion of the momenta. So, this is basically the RL combination if you wish. You can have the electron left handed, the spin is aligned opposite to the momenta. So, this is L, but the tau is right handed, or you can have both spins projecting opposite to the incoming momenta. This is the vertex. So, you can have both left handed. Okay. So, this is what are the combinations that we have. Here, I would also like to mention that when we were drawing the Feynman graphs, I told you that when the momenta and the spin flow, so roughly we were talking about this kind of terminology, that when those are aligned, that is going to give you the particle identification, and when they are opposite, that is actually going to give you anti-particle identification. So, it must not be confused with the helicity combination. Okay. So, it is just to distinguish between the particle and anti-particle, but each particle. So, for example, if you look into the Feynman graphs, so here we have this arrow on the fermion line which is actually aligned with the direction of the motion. So, this is just to note that this is a particle, this is not an anti-particle. Okay. But this will actually have 2 possible helicity combinations where actually the spin can be aligned along the momenta or spin can be aligned opposite to the momenta. So, you can say that this is denoting the fermion flow, but actually the spin flow will actually give you the helicity combinations for each of these initial and final states. I hope it is clear that, so therefore, there are 4 helicity combinations that you actually have for this electron tau collision. So, absent any specific polarization, we need to take an average over it. So, that average over the spin projections of the initial state, right. So, that is why this factor of 1 by 4 is coming while you are actually summing over all possible helicity combinations. And now we must remember that for each of these initial spin or helicity combination, there are 4 different final state spin and helicity combinations which are possible, which we have to take into account in order to calculate the cross section. So, for example, when we talk about mod of MRR square, where I have already assumed that I am actually going to take the combination of the right helicity combination of the initial state particles. For that, I actually have to take a sum over all possible helicity combinations in the final state. So, that is what I will be writing here, that M mod of MRR square essentially means sum over all the helicity combinations of mRr square. What does it mean? It basically means that you have to take all these combinations, that mRr going to RR, where both the final state electron and tau are right handed, RR to RL, RR to LR, and RR to LL. So, this essentially what is indicated by mod of mRr square, which actually has to be summed over all the final state spin or helicity. So, what does it mean? That mod of m bar square, that is essentially 1 by 4 of all the sum of the different combinations like mod of mRr square plus mod of mRL square plus mod of mLr square plus mod of mLl square. So, in this notation, the initial state helicity combinations are explicitly mentioned, not the final ones, and you understand that when we say that we have mRr square, that basically means that you have mRr to RR square plus mRr to RL square plus mRr to LR square plus mRr to LL square. Similarly, mod of mRL square is mRL to RR square, RL to RL square, RL to LR square, and RL to LL combination. So, let us write one of these. What is mLR mod square? तो इसका मतलब basically you have LR to RR, you have LR to RL. There is no price of writing them in the same order that I am doing. Your results will be invariant in what order? I mean, it's a sum ultimately. But you have to take all possible combinations, and similarly LR to eventually LL mod square. And finally, you have the combination for MLL. I am not writing it, I am just writing that this is MLL to RR mod square plus the other combinations which we just wrote. So, this whole thing is what is embedded in this matrix element square mod of m bar square. So, let us come back to this particular process for which we were trying to calculate the matrix element square, which is E minus tau minus going to E minus tau minus, which is the matrix element is given by minus E square by Q square U E bar P3 gamma mu U E P1 into U tau bar P4 gamma mu U tau P2, right. So, this is what we actually had. Now, first thing that we have to do in order to find m squared is to find m dagger, right. So, what is the m dagger? M dagger will be for multiplication of two matrices A and B, m dagger will be B dagger A dagger. So, this has to be daggered, this dagger, and then this has to be daggered, this dagger is this one. So, you have basically U tau bar P4 gamma nu U tau P2 dagger into U E bar P3 gamma nu U E P1 dagger. You deliberately see that I had the Lorentz index nu which was summed over here, and it was a dummy index, just not to confuse that I must not use the same Lorentz index when I do take the dagger. So, I rather do therefore use gamma nu, but you also have to make sure that this nu is a dummy and summed over, like this nu gamma nu which is sitting in the covariant and contravariant index is the same. I mean, there is nothing specific about nu. For example, there is nothing specific about mu here. You can use any index. Similarly, there is nothing specific about nu here, but the point is this index must be a different one from the one that you have used for writing the original matrix element. So, this is what m dagger is. So, you can basically say that then I can organize. So, see, this is therefore you can say that I can organize these terms by summing over the electron spin. Under the sum of electron spin, I can actually organize the terms which involves only the electron spinners. So, originally we had U E bar P3 gamma mu U E P1, and after taking the dagger we have this term which is U E bar P3 gamma nu U E P1 dagger. So let's write partially for that one for the tau spin. So for tau spin, the original one u tau bar P4 gamma mu u tau P2, right, and then the dagger u tau bar P4 gamma nu u tau P2 daggered. Okay. So now you can see that the part that I have to understand or estimate is essentially this part. What is the dagger of this current u e bar P3 gamma nu u e P1 dagger? इसका मतलब क्या है? So let's try to find out the generic expression. So let's write psi 1 bar gamma mu psi 2 dagger. So if I take this psi 1 bar gamma mu psi 2 dagger, so psi 1 bar by definition is psi 1 dagger gamma 0 gamma mu psi 2 dagger. And once again, when we take the dagger of a matrix, we all know that it's actually the dagger comes in the reverse direction. So it will be psi 2 dagger gamma mu dagger gamma 0 dagger psi 1 dagger is psi 1, right. Now what I am going to do, that I am going to actually, using the fact that gamma 0 square is essentially identity, so therefore I am going to insert one gamma 0 square at this position. Okay. So I have inserted one gamma 0 square, and then I had this gamma mu dagger, gamma 0 dagger, etc. Then I am also going to use the fact that gamma 0 dagger is gamma 0, and if I do that, so this basically will mean that one of these gamma 0 when actually combines with the psi 2 dagger is going to give me psi 2 bar, correct, and then one of this gamma 0 is actually left, that is what I have, and gamma mu dagger, and this gamma 0 dagger is becoming gamma 0 here. So I have psi 2 bar gamma 0 gamma mu dagger gamma 0 psi 1, and psi gamma 0 gamma mu dagger gamma 0, this quantity you can verify to be gamma mu itself. Okay. So therefore what we actually have out of this calculation, that this calculation shows that this is psi 2 bar gamma mu psi 1. So the bottom line is that whenever you have psi 1 bar gamma mu psi 2 whole dagger, you essentially flip the position and you essentially have psi 2 bar gamma mu psi 1. So then tell me what is going to happen to these daggers that we actually have in the matrix element square. We have u e bar P3 gamma nu u e P1 dagger, उसका मतलब simply होगा u e bar P1 gamma nu. I do not have to think about the dagger of gamma nu anymore, because that I have to taken into account by this exercise that we have done here. So using this is simply u gamma nu u e P3. What happens to u tau bar P4 gamma nu u tau P2 dagger? This is going to be u tau bar P2 gamma nu u tau P4. Very, very good. Now using these two I am going to write so the matrix element square that we actually wrote before. So you have the original one u e bar P3 gamma mu u e P1, and the dagger of it will give you u e bar P1 and gamma nu u e P3. And similarly for the tau spin part, we have u tau bar P4 gamma mu u tau P2 u tau bar P2 gamma nu u tau P4. Now what you can say that these two and these two combines to two quantities. So you have not bothered about this previous part, like this is there already 1 by 4 e to the power 4 by q to the power 4, that is obvious. So what you actually have, that you have basically, you can call L E mu nu. So you call this quantity, you see that there are two Lorentz indices, right, mu and nu. You call this to be L E mu nu, and you call this quantity to be L mu nu tau. So then your matrix element looks like this. Now, what I have to do, that I have to basically see what happens to this sum over electron spin. Okay, so it seems that the time is over today, and I am going to stop here, and I am going to carry on the calculation in the next lecture. All right, so stay tuned. Thank you very much.